This meeting is being recorded.
In Chapter 8, Problem 28, we see an example of an anti-dihydroxylation reaction. And we know that from the reagents that are listed. So these alkenes will first be treated with a peroxy acid, which has this general form here. So we have different R groups. So first step, we would form an epoxide, right? So that three-membered ring with oxygen in it. And then we would follow that with step 2 here with treatment with aqueous acid. So in that step, we'll have ring opening, and we would add these OH groups. So the dihydroxylation means that we're going to add 2 of these OH groups in an anti fashion. So one in the front of the plane, one in the front of the double bond, one from the back. So and the ring opening step follows proton transfer, followed by nucleophilic attack by water, and then one additional proton transfer to give our final product. So let's take a look at A here, and we can place this methyl group on a wedge, and I'm going to place this methyl group on a dash, and we're going to add to this double bond our 2 hydroxides. So we have this on a, we can put our OH on a wedge here, right? And then we'll put our OH here on a dash. All right, so that's it. So around the double bond, we don't have to think about radio specificity, just stereo specificity for these 2 compounds. All right, so next up we have B here. Oh, sorry, we can't forget the enantiomer as well. So with compound B, we're going to form an epoxide and then open that ring, and that double bond would disappear. Sorry, I forgot to mention that. No more double bond here. So the second compound, we would have 1 OH that adds in from this face, and then we would have our other OH that adds from that face, plus the enantiomer. All right, so just remember there's no double bonds in our product here, so we'll get rid of all of those. Okay, so let's take a look at our reaction with molecule C here. So we'll have on one side of our double bond, we'll have our hydroxide on a wedge. On the other side, we'll have OH on a dash. Now what happens here, we don't actually have any chiral centers created. So our OH will just add on this side as a single bond, and then over here as a single bond. So we don't have to think about chirality or stereochemistry with this specific example because we do not create any chiral centers in our product. Example E, so once we remove that double bond, we're going to add on a wedge, OH on this side, we're going to add on a dash over here. Now, what you might notice is due to this being a single bond and free bond rotation, we can actually end up with a meso compound. So both of these OH groups up top here are in the same plane, and then due to the symmetry within the molecule, this would be an achiral compound, even though there's chiral centers. So that's our first and only meso compound as a product. So let's look at F here. Let's put that methyl group on a wedge, and then we'll add 1 OH on this side on a dash, and then this OH down here I'll add on a wedge, and these are our products. We forgot to add the enantiomer to this one, right? This had no chiral centers with D, so there's no enantiomer. This one also has an enantiomer, right? Any chiral centers, so A, B, C, and F, they would all have the enantiomer with their product.